Okay, so this is a little companion video that I'm putting together that I'm hoping will help us really internalize our knowledge about nucleotides and nucleotide structure. And basically what we're going to do together in this video is just learn our nucleotides by drawing them out. And I personally have found that drawing the nucleotides is a really good way to internalize their structure and the different Watson-Crick-Franklin base pairing interactions that the nucleobases can perform. And I think it's a little bit easier, at least for me, to do it this way than to just try to stare at pictures of them and just try to memorize that. So let's go ahead and learn a little bit about our nucleotides and how to draw them. So I think the best way to start with how to draw a nucleotide is to start with the sugar. And that's because everything else about our nucleotide is basically attached to the sugar. And so there are 5 attachment points to this sugar, and I will label them all here for you in the standard numbering. There's the 1 position, 2, 3, 4, and 5 prime positions of our sugar. And this numbering is very useful because to make a nucleotide, what we need to do is attach a nucleobase to the 1 prime position. Okay. The 3 prime position will always have a hydroxyl group, like you see here. The 5 prime position will vary depending on whether this is a nucleotide or a nucleoside. And the 2 prime position will also differ depending on whether this is a DNA or an RNA. So with respect to the 2 prime position, if X equals H, then we have ourselves a DNA nucleotide. And if X equals OH, we have ourselves an RNA nucleotide. Similarly, over here, if R equals H, that is, this is just a hydroxyl, then we have a nucleoside. And if instead our R is a phosphate, or some sort of phosphate group, then we have ourselves a nucleotide. And so as long as we can just quickly whip out this core for the nucleotides out there, we're in pretty good shape. So you should be able to sit down and right away, if I said, let's draw an RNA, we should know that we're going to have base. I said it's RNA, so there's an O and a OH there. And let's say I told you it was a nucleoside, then we know this should be an OH. On the other hand, if I told you to draw a, so this would be an RNA nucleoside, okay? But on the other hand, if I said draw me a DNA nucleotide, well, we can again start with our sugar base. We know there's going to be a nucleobase here. We know there's going to be an OH here. And in this case, we know that since it's a nucleotide, there's going to be a phosphate group attached there. And since it's a DNA, the 2' hydroxyl position is going to be an H. And so this is a DNA nucleotide. Okay? And so basically, if you can just really lock in your ability to draw this portion of the molecule, you're going to be in great shape because everything else is sort of a derivative of just assigning the right parts to this kind of modular framework. Okay, so as long as you can draw your nucleotides, you're pretty much most of the way there. And the only thing that really remains in order to internalize these nucleotide structures are your bases. And admittedly, this is a little bit annoying because there is some components of memorization here that you need to do in order to learn your purines and pyrimidines. But if you kind of structure your thinking about your bases in your mind, then you can kind of easily organize the different structures that you're going to see. And so what I like to do is first categorize the bases in my mind into purines and pyrimidines. And this is of course natural because purines are always going to form base pairing interactions with pyrimidines. And so it makes sense to think about purines and their complementary pyrimidine or vice versa. To be able to draw these, what I like to do is simply start by just knowing what the back, kind of the overall skeleton or backbone of the different rings of these is. And so I always start, when I draw one of these, with the nitrogen that's involved in making the glycosidic bond to my sugar, and then I build the rest of the ring up from there. So in the case of the purines, that 9-membered ring looks like this. Okay. And at this stage, I don't draw the double bonds. I just draw it like this so that I know that I've got the core structure right. And then after I put in different donors or acceptor groups onto this backbone, then I fill in the rest of the double bonds. Now on the pyrimidine side, I do the same thing. I draw my primary nitrogen that's going to be making the glycosidic bond. And then I draw the rest of the ring, so like so. And for these pyrimidines, there's always going to be a double bond in this position because there's no nitrogen over here. And for all the nucleotides we'll be discussing, there's also always going to be a carbonyl in this position. And so this is kind of where I start when I have to draw either one of them. I draw this for the purines and I draw this for the pyrimidines. And then the other thing that's useful when you've got it in your mind this way is you can highlight in your mind the places that are going to change. And so on the purine, the things that are going to be different are going to be what's substituted at this position, whether or not this position is going to be protonated or not, and whether or not there's going to be a substitution at these positions. So these are really the, if you know the purine backbone, then you just only need to know what's going on at these 3 positions to be able to draw your adenine and your guanine. Similarly, on the pyrimidine, pretty much the only variable position is going to be here, whether or not you have a donor or acceptor in this position, which is in turn going to set whether or not this nitrogen is protonated or not. And that's pretty much it. Now I'll add that it is the case that thymine in DNA has a methyl group at this position and doesn't have a methyl group at this position in the corresponding pyrimidine uracil in RNA. But for the most part, the things you'll want to really focus on are these 2 positions in the pyrimidines or these 3 positions in the purines. And so from this scaffold, we can now go ahead and draw all the nucleotides. Okay, and so let's go ahead and now, using our backbone skeleton for the purines and the pyrimidines, let's draw each of the nucleotides, in this case for DNA, for adenine, guanine, thymine, and cytosine. And what we're going to actually do when we draw them to help us, again, kind of memorize what's going on in terms of the corresponding Watson-Crick-Franklin base pairing, is we're going to draw them side by side so that we can actually see those hydrogen bonds form. And that will be helpful to internalizing these structures. So let's draw really quickly again the purine backbone for both of these. So we've got our base structure, and we'll do the same thing here. Glycosidic bond. Okay, so we've got our 2 structures here. And as I mentioned before, the places where we're going to get variation are going to be in the purines these 3 positions here. Okay. And for me anyways, one convenient, I always start at the top because this is, I think, just for me how my brain works. And I always remember that adenine has an amino group at this top, adenine with an A, amino here. And so let's go ahead and substitute in on this ring an amino group there. And if there's an amino group here, then that means that there's going to be a lone pair on this nitrogen position. And in the case of adenine, there's no substitution at this slot. And so from here, we can go ahead and draw the remaining double bonds in our structure, like here. And this completes our adenine nucleotide. Now we can do the same thing for guanine. And so if adenine has an amino group at this position, then that means guanine is going to have a carbonyl group at this position. So we can go ahead and draw that carbonyl in there. And because we have this double bonded O right here, we're not going to have a double bond right here with the nitrogen. And so instead, this group here gets a proton, like you see here. And then as I mentioned, this group here can also have a substitution on it. And in the case of guanine, that is another amine. Okay, so once we draw it in like this, then it's pretty much, we just fill in just as before, and now we have our guanine nucleotide. So now let's see if we can actually take advantage of the fact that we've drawn these structures to help guide us in terms of building the structure of the corresponding pyrimidine. So let's start by, again, drawing the kind of the pyrimidine backbone structure. So we've got our nitrogen there, and we've got a nitrogen there. And as I mentioned, we always have a double bond there, and we always have carbonyl here. And similarly for the cytosine, we'll have a nitrogen here, which is part of our glycosidic bond. And then we're going to have the other nitrogen here. And we'll have the double bond, which is always present. And we'll have the carbonyl, which is always present. Okay? And so as I mentioned before, the areas to look at for variation are here, and here, here, and here. And so if adenine is going to make a base pair with thymine, are we going to put an amine, or are we going to put a carbonyl here? Well, this is acting as a hydrogen bond donor, so it makes sense to put an acceptor here, and really the only acceptable acceptor is the carbonyl group. So we will put a, should have drawn that in red, sorry about that. We will put a carbonyl group here at this position. And because we put a carbonyl group here, we're not going to put a double bond here, and that means that we're going to put a hydrogen here, which also should have been obvious to us, because if this nitrogen has a lone pair and is acting as a H-bond acceptor, then we better have an H-bond donor in this position. And so without really actually even having to think about it, by simply filling in the hydrogen bonds that we expect to form with the adenine scaffold, we were sort of able to derive the thymine structure that you see here. And the only other thing I should point out is that in the case of thymine / uracil, because they have essentially the same, the thymine is going to have this methyl group in this position, whereas for uracil it would not. Okay. Now let's see if we can do the same thing from cytosine. So our guanine has a carbonyl group here, which is a H-bond acceptor. It has an NH here, which is an H-bond donor, and it has another H-bond donor here, which can obviously already base pair with the carbonyl group we see here. And so again, the two areas that we want to ask ourselves are these positions right here. And if we have a carbonyl group, then obviously what we're going to want to put in this position, I'll use red, sorry about that. We're going to want to put an amine group here, because then it can act as a hydrogen bond donor to interact with the carbonyl H bond acceptor. And similarly, because this nitrogen has a proton, it is an H bond donor. Therefore, we would expect this nitrogen here to be the H bond acceptor, and we'll get a hydrogen bond that forms between here, and a hydrogen bond that forms between here. And as we mentioned, those three are going to form a hydrogen bond. And because now we don't have this carbonyl group here, we can put another double bond in this position so that the ring is going to be fully planar now. And so I hope you can see that from this, if we just start with our purine and pyrimidine scaffolds and even invoke just one simple memory device like adenine, the A means amine, in this position, we can pretty much reasonably figure out what the associated substitutions on the pyrimidine ring are to give us our two H bonds. And similarly, if there's no amino group in this position, instead there's a carbonyl, we've got guanine, and we can easily draw the rest of the ring here and form our three H bonds here. And so, at least for me, now of course, if it's easier for you to just brute force memorize these structures for yourself, that's fine. But I find that this is a useful way of organizing the information for me, because we start with the purine and pyrimidine scaffolds, and then we decorate it with the appropriate groups to give us the adenine or guanine, and then we try to remember those substitutions in the context of the base pairing interactions that we care about anyways.